Okay, let's start today with this little problem right here, trying to find a volume below a three-dimensional surface and above the region in the XY plane bounded by this. And so let me draw this first, the XY plane, because that's what we usually call our D, area D. Yeah, so in this case, we're going from y equals x squared, or between y equals x squared and y equals 8 minus x squared, which minus x squared up 8. So you can get that pretty quickly here. So this is the region D here we're talking about, the area bounded there. Okay, so we're going, we've got this surface, whatever it looks like, we don't even have to draw it. So we've got this three-dimensional surface, whatever it looks like, and we're projecting then from this up to that surface, from the XY plane. I'm going to draw the whole deal out, but we're taking that in the XY plane here, which would, be the flat surface, and then we're going up to whatever this surface looks like. That's what so we're taking that surface up to that region, up to that surface. We want to find that volume. Well, we just so happen to have a tool that can do that, right? The old double integral. The volume, the double integral over this D of my f of x, y, dA, which we write it that way because sometimes we integrate first with respect to y, sometimes we integrate first with respect to x. So dA, but that gives us that volume. Gives us that volume of whatever, shape that is. It's a kind of a weird looking shape probably, but anyway, double integral. Now we just got to put in the fine details here. And in this particular case, it looks like, these are functions of x, so what would I integrate first with respect to? Go from here up to here. From this y value up to this y value, right? So integrate with respect to y first. My f of xy is this 16xy plus 200. So integrate with respect to y first, then the x. Okay, and so the y's are going to go between, it's going to go from the low is 8 minus x squared, x squared. X squared is down here, even though I wrote the 8 minus, probably should have wrote the other way around. The low one is the x squared, so that's the low limit for y, and then it goes up to the 8 minus x squared. Now the other thing, the x's, all right, so the x's are just going to go from this x value to this x value, so I just have to figure that out. How would I figure that out? How would I figure out those x's? Well, it's where the two intersect, set the two equal. And usually they're pretty nice, you can probably guess them, but just to be sure, add the x squared, you got 2x squared equals 8. Divide by 2, and you got x squared equals 4. So probably what we thought. That's x is plus or minus 2. Right? Okay. All right, so those are my limits. The y's go first, so it's x squared to 8 minus x squared. And then the x's go from -2 to 2. So we integrate first, the innermost here first, so integrate with respect to y first. Nothing too bad there. What would that be? The 16x would just be a constant, so it'd be 16x times the 1/2 y squared, the antiderivative there. Antiderivative 200, be 200y. And then we're going to plug in x squared and 8 minus x squared, or 8 minus x squared and x squared. Then that's 8xy squared, so, okay. A little bit of a deal, but, so this goes in for y, so it'd be 8x times 8 minus x squared, and then it'd be 200, plug that in for y, 200 times 8 minus x squared. And then I'd do it all over again, plug in the x squared for y, so that would be 8x times x squared squared, x to the fourth, plus 200 times x squared. And then just clean that up, and we'll have it. I guess the biggest thing would be this squared, 8 minus x squared squared, which would be, what, 64 minus 8x squared minus 8 would be minus 16x squared, plus x to the fourth, but then I'm going to throw in an 8x, so that all turns out to be 64 times 8, 512, is that right? X. 8 times 16, 108, and the x cubed, and 8x to the fifth, plus. All right, then back here I'll have minus 8x to the fifth, oh, look at that, minus 8x to the fifth, and minus 200x squared. I'd get that to cancel out there. Oh, I missed part of it too, didn't I? Forgot this part. There also should be a plus 1600 in there, minus 200x squared. There, before that, so here's what I got. So that, the only thing that combines, it looks like, is, well, those go out, but these make a minus 400x squared. I did that right. Yep. So let's write in order. Minus 108x cubed, minus 400x squared, plus 512x, plus 1600. Now we just have to do it with regard to x. It'd be minus 108 divided by 4, x to the fourth, minus 400 thirds, x cubed, plus 512x, divided by 2x squared, 1600x, from -2 to +2. I think that's just going to double it up, so. Negative, does that go in? Yeah, that goes in nicely. 27, right? Be minus 27 times 16, minus 103rd times 8, plus, that'll be 256 times x squared times 4, plus 3200. And then I think we get the, pretty much exact same thing. Minus 27 times 16, minus 400 thirds, times 2 to the third, -8. Plus 256 times 4, and then minus 3200. I think, all right, so that'll be a plus, so that'll cancel that. And then that'll make that a minus, so that'll cancel that. I think what I wind up with is this, negative 3200, negative 3200, so it'll be minus 3200 thirds. You got plus 3200, then you got minus 3200 thirds again, and plus 3200, so Anyway, it's just a little bit of a lengthy ordeal there, but not too bad. Which I get to be 12,800 over 3. All right, any question or concern? So yeah, the big thing on that is, yeah, this does represent a volume. So what we're finding there, it's a volume. All right. Now, one other point to be made on this section right here. Is this. You know, this area D, general region, which sometimes we do with the, so let's say we got this y equals some function of x. Call it f1x, and then y equals f2 of x. The other way. I think I call them G2, but it doesn't matter. Call that area D. Call that area D. Well, one other quick little point is we can get that area of D by doing a double integral. And it's just simply the double integral over D dA. You're saying, what? What does that mean? Here's what I'm saying. So the function here is just basically it's a 1. That, if I just double integrate over D 1, that the function is 1, that's going to give me the area of D. Now, how I can prove that fairly easily to you is because I'm just talking about the area between two curves right here, aren't I? Which we did in Calculus 1. The area between curves is you just integrate, you do the upper minus the lower from A to B. Right? And that's the area between curves. Well, that area between curves is now what we're calling it as D. And notice what I get if I do this, all right? So if I do this double integral like this, I mean, we could have it the other way. But this is, so I would do the y's first, then the x's, and again, I'm just integrating 1. And so I would go from the lower limit f1 of x to f2 of x, and then the x's go from a to b, doing the y's first. So if I do that integral, the integral of 1 is just y, since I'm integrating with respect to y, then I would do that from f1 of x to f2 of x. And notice if I plug that in for y, I've got f2 of x, and then plug it in f1 of x. Okay, yeah, so it's the same thing, get the exact same thing. So just make note that if I just do the double integral, don't have the function being 1 there, what that gives me is just that area. It doesn't give me a volume, it just gives me that area. Okay, question or answer?